We're now going to look at another example of calculating probabilities. Then we'll use this example to illustrate some properties of probability. What we're looking at is a bag of M&Ms that contains the following breakdown. 7 red, 4 yellow, 7 orange, 2 green, 3 blue, for a total of 23 M&Ms. We're going to find the following probabilities, starting with the probability of selecting a blue. So again, we're just selecting one M&M from the bag, and we want to know if we randomly select an M&M, what is the probability it's blue? Probability is a ratio of success to total, so we can successfully select a blue M&M 3 ways out of 23 M&Ms in the bag, so the probability is 3 over 23. Next, let's look at the probability of selecting a red or a green. Well, if you're thinking that it's 9 out of 23, you're absolutely correct. Let's take a look at how we got that probability. Remember OR. That's the key word for that union, which means everything in one set or the other. So it makes sense that we would take the 7 red, add it to the 2 green to get a total of 9 successes, and then of course out of 23 M&Ms. Now, why didn't we have to worry about subtracting anything? Because remember, we said with the union, it's okay to start out by adding the number in each set, but if there was any overlap, you had to subtract it, otherwise you'd be double counting. Well, think about it. There is no overlap between the red and green M&Ms. If it's a red M&M, it's red. If it's green, it's green. It will not fall into the other sets. So the set of red and green are disjoint. That's why we were able to just add the 7 to the 2 and be on our way. All right, next up, we're randomly selecting one M&M from this bag, and we want to know the probability we get a purple. Well, looking at the breakdown, we see that there are 0 purple in the bag, so we have a 0 chance of success out of 23 M&Ms total. So, simplifying it, we see the probability is 0, or you could say you have a 0% chance of success. Now, what's the probability of randomly selecting an M&M? Well, if you reach into a bag of M&Ms, with 23 in there, you have 23 chances of success out of the 23 total M&Ms. In other words, the probability is 1, or if we convert that to a percent, it is 100%. You are 100% certain to get an M&M out of that bag if you select a candy. Okay, lastly, the probability of not yellow. Take a minute and calculate that probability of not yellow. Now, hopefully you came up with 19 over 23. What I'm interested in is how exactly you calculated that 19 over 23, because we really have two choices. On one hand, we could have just went to the list and selected everything that was not yellow. 7 red, 7 orange, 2 green, 3 blue, which gives us, if we add that up, a total of 19 successes out of 23 M&Ms, and that's where we get our 19 over 23. But there is another way that we could have calculated it. Instead of adding up what we wanted, we could subtract what we don't want. Think about it. There's 23 M&Ms total in the bag. If we just remove the 4 yellow we don't want, that will result in the 19 successes of not yellow, and then over our 23 total possible outcomes. So keep in mind, sometimes you can add up what you do want. Sometimes you can subtract what you don't want. If you have the choice, if you have enough information, just do it one way. You don't need to do it both ways. But make sure you're flexible in your thinking, because sometimes you may only have enough information to add up what you want. And other times you may only have enough information to get rid of what you don't want. So just realize there's two ways of handling that. And when you encounter it, just do whichever way you have the information in order to be able to complete that, that probability. Okay, next we're going to use this M&M example as a way to illustrate the properties of probability. Our first property, number 1, says that if capital E is equal to E sub 1, E sub 2, E sub 3, then the probability of E is equal to the probability of E sub 1 plus the probability of E sub 2 plus the probability of E sub 3 if E sub 1, E sub 2, E sub 3 are disjoint. Well, that's a whole lot of alphabet soup. Let's break this down and let's understand what all this notation is saying. First of all, it's saying that if we have an event, capital E, that's made up of smaller events. Well, back in our M&M example, we did. We had the example of selecting red or green. That's the capital E. That's our all-encompassing event. And the smaller events, the E sub 1, E sub 2, was getting red, getting green. What this property tells us then is if we want the property of the all-encompassing event, take the probability of the smaller events and add it up. And that's really what we did. In order to get the probability of red or green, which we knew was 9 over 23, we could take the probability of getting red, which was 7 over 23, and add it to the probability of getting green, which was 2 over 23. So our all-encompassing event, red or green, could be found by adding the probability of the smaller events that made it up. And again, we didn't have to worry about subtracting anything because the sets were disjoint. There was no overlap between the red and green M&Ms. Okay, next up, let's take a look at number 3. We'll come back to the properties talked about in number 2 in just a few minutes. But let's take a look at the probability of S. P of S equals 1. What does that mean? Well, remember, S is your sample space. So this is just simply saying the probability of being in your sample space is 1. Well, that's what we noticed when we did part D. The probability of getting an M&M. Getting an M&M, that was everything in our sample space, which we saw carried a probability of 1 whole or 100%. Another way of thinking about it is applying this property from number 1. Our all-encompassing event E is actually being in our sample space, getting an M&M. The smaller events are red, green, yellow, blue, orange. So if we take the probability of all those smaller events, the probability of getting a red, the probability of getting a yellow, the probability of getting an orange, probability of getting a green, probability of getting a blue. These are all the smaller events that make up our all-encompassing capital E, or being in our sample space. If we add up all those probabilities, notice what we get. 23 over 23, or 1 whole. So this is just saying the chances of being in your sample space are 1 or 100%. Next, let's take a look at the property stated in number 4. This says the probability of E prime is equal to 1 minus the probability of the event. Well, recall what that prime means. That prime means the complement. So this is saying that the probability of the complement is 1 minus the probability of the event. Well, we were finding a complement in part E. Not is the key word for the complement. So in part E, when I asked you to find the probability of not yellow, I could have just said the probability of the complement of yellow. Now think about what we did when we calculated that probability in part E. We said that we could add up what we want, but what I'm interested in is when we subtracted what we didn't. If we look at this fraction, 23 minus 4 over 23, if you recall from work with fractions, when you have a single term in your denominator, you can actually create separate fractions. In other words, I can make the fraction 23 over 23, and then minus, because there's a minus sign, 4 over 23. So I can split that numerator into 2 separate fractions. Now consider what each of these fractions represent. 23 over 23 is 1 whole, or the chances of being in our sample space. 4 over 23, that is the probability of getting a yellow. So notice, the probability of the complement can be found by 1 minus the probability of the event. And that is precisely what property number 4 is telling us. So you've been working with complements and finding the probability of complements, applying that rule all along. Same thing with the property in step 1. You've been doing it all along. All we're doing now is putting the formal notation to it. Okay, lastly, let's take a look at what statement 2 is saying. So statement 2 is this string inequality. What it's saying is that the probability of an event is greater than or equal to 0 and less than or equal to 1. In other words, all probabilities will live between 0 and 1. A probability can be equal to 0, it can be equal to 1, or anything in between. But it cannot exceed 1, and a probability will never be less than 0. So that's what this is saying. But what I want to look at it is why. Why is it we cannot live beyond 0 or beyond 1? So why can't a probability be less than 0 or less than 1? Or greater than 1, excuse me. Well, this boils down to looking at the definition of probability. Remember, probability is a ratio of success to total possible outcomes. So if we're looking for the probability of an event, we want to find the number of ways the outcome can happen and put it in ratio to the total number of possible outcomes. Well, let's start with if the probability was less than 0. Numbers that are less than 0 are negative, which means in terms of a fraction, either the numerator needs to be negative or the denominator, one or the other. Well, in order for a probability to be negative then, that could imply a negative amount of success. Does that make sense? I mean, I've heard of having absolutely no success before, but a negative amount of success? Imagine you got an exam back and it said that you got a negative 26%, right? So yeah, it's possible to get a 0% on an exam, but to get a negative, that doesn't happen. So you can either have absolutely no success, but you would never have a negative amount of success. Let's consider now being over here. What if the probability was greater than 1? What would that imply about our fraction? Well, the only time a fraction is greater than 1 is when the numerator exceeds the denominator. So when we have an improper fraction.